In this video, I'm going to talk about the chain rule for derivatives. Let's consider a function f. Let's say f is differentiable at some point c. That means f prime of c exists. Let's say g is another function such that it's differentiable at some point b, where b is f of c. Okay, so f is differentiable at c and g is differentiable at f of c. Then we make the following conclusion. Conclusion number one is that g composed with f prime of c exists, and the second conclusion is that g composed with f prime of c is gonna be equal to g prime of f of c times f prime of c. To show this, we are going to use the basic or the fundamental definition of derivative. The definition of derivative is this. For some function u of x, the derivative is defined as, or u prime of x is defined as limit h approaches 0, u of x plus h minus u of x divided by h. This is the standard definition that you are used to. However, a slight variation of the same definition is this guy. U prime of x is limit x approaches c, that means, which is kind of like x minus c approaches 0, right? So x approaches c, u of x minus u of c divided by x minus c. These are equivalent definitions. So we are going to use that. Now we are going to apply this definition to actually the composition of these two functions g and f. Now if we apply that definition of derivative to the function composition g composed with f prime of c, this is what we get. Limit x approaches c, g composed with f of x minus g composed with f of c divided by x minus c. Now, by using the definition of composition of functions, this is what I get. So this term becomes g of f of x, and this term becomes g of f of c, and in the denominator I have x minus c. At this point, what I do is this. I multiply the numerator and the denominator by f of x minus f of c. So this is what it is. So if you kind of reorganize the terms, you get the numerator divided by f of x minus f of c, then times f of x minus f of c divided by x minus c. At the end, if I simplify it, I get back what I have had. Now, we have a limit of product of two expressions, or you can think of it as two functions, which is going to be the product of the individual limits. That's exactly what I have here. So I have the limit of the first fraction, okay, which is this one, times the limit of the second fraction. At this point, look, this is nothing but the f prime of c, right? F prime of c. Now, the introduction of f of x minus f of c created a little bit of problem. The problem is that it is showing up in the denominator. What if f of x minus f of c is equal to 0, or equivalently f of x is equal to f of c? In that case, we have a problem. We have division by 0. So this is a big problem. However, for the sake of argument, let's assume that that is not the case. So in any neighborhood of c, okay, any neighborhood of c, so let's say c is a point right here. This could be a neighborhood, or this could be a neighborhood. Doesn't matter how small the neighborhood is. We can get arbitrarily close to c, as close as we want. And there will be no situation where f of x is going to be equal to f of c. Then we are kosher, we are fine. we have nothing to worry about. So the denominator is not going to be 0. We know that f in and of itself is differentiable at point C, right? F is differentiable at point C, so f prime of C exists, means that f is also continuous at point C. So f is continuous at point C because differentiability implies continuity, point C. So in that case, if f of x is not equal to f of C for any neighborhood of C, we are good. And then what we get is this. So the left limit is nothing but g prime of, by the way, f of C, g prime of f of C by definition, and the right limit is f prime of C. This is exactly what we claimed, by the way, g composed with f prime of C to be equal to. So we are good. However, the problem is that the denominator right here could be 0. How do we deal with that situation? To address that situation, we are not going to assume only that there are just one or two neighborhoods of C. So let's say this is my C. There are just one or two neighborhoods of C where f of x is equal to f of C, which is equivalent to saying that f of x minus f of C is equal to 0. That's going to make this denominator 0. But rather, we are going to assume that we are going to assume the extreme case. In every single neighborhood we can potentially think of, as close to C as possible, each of them will have at least one value of x such that f of x is equal to f of C. Now, we can do that by creating a sequence. Let's call this x1 is a neighborhood 1, x2 is the value in neighborhood 2, x3 is the value in neighborhood 3, ... and xn in the neighborhood of neighborhood n is the point that is going to give you f of xn is equal to f of C. So for each of these neighborhoods, and it keeps going, we have a point that is going to make it 0. That means f of x minus f of C to be 0. If that is the case, this sequence, we are going to be using it to find the derivative. So let's say f prime of C. So for that particular point of interest, f prime of C is going to be limit x approaches C, okay? F of x minus f of C, all of it divided by x minus C. But look, this is going to be the same if we go through this sequence, okay? Instead of x approaching C, we can make these neighborhoods as close to x as possible, okay? For simplicity, you can think of the difference between x minus C, absolute value of it is less than 1 over n, okay? And n is going to be actually x sub n here. X sub n minus C is less than, absolute value of it is less than 1 over n. And as n gets bigger and bigger and bigger, we can shrink this, okay? So we could say limit x approaching C is the same as xn approaching C. No problem at all, okay? It's a sequence. X approaches C, it could approach C using any number of sequences, literally infinitely many different number of sequences. Doesn't matter. That means it's going to be f of xn minus f of C divided by xn minus C. However, keep in mind that f of xn is equal to f of C because these are the points where f of x is the same as f of C, which means my derivative is nothing but 0. So my f prime of C is equal to 0. This is an important conclusion that we will need later on. Here, if we can somehow show that this derivative g composed with f of f prime of c is 0, then we are okay, we are done for the situation when the denominators are the same. That means right here, f of x minus f of c is equal to 0. However, this logic that we just applied right here for this guy cannot be applied to this, because we really don't know what the limit is or whether it even does exist. So to address this issue, we are going to introduce a concept called finding supremum. You may already know about it. If you already know, then you know exactly what I am talking about. But in case if you do not know, I'll give you an example. Here is an example of a supremum. So think of this sup of some set. So my set is going to be set of numbers or sequence of numbers. 0.9, 0.99, 0.999, 0.9999, and it keeps going. As you can see, these numbers are increasing. This is a sequence. Okay, this sequence is increasing, but increasing to a value which is 1. As you can see, it gets arbitrarily close to 1, but it never is equal to 1. None of the elements in this sequence is 1. Therefore, the supremum of this sequence is going to be 1. That means the extreme case. In the extreme case, or in the limiting sort of sense, the value that it reaches is 1. So the supremum is 1. And similarly, you could think of infimum of a set. And let's say my set is 0.01, 0.001, 0.0001. Actually, this is a sequence and it keeps going. As you can see, infimum, as it kind of implies the name, the smallest value that this set of numbers or this sequence approaches. And as you can see, all of these numbers are getting smaller and smaller and smaller, and so the infimum is going to be 0. We are going to be kind of using similar argument here. Let's consider the supremum of this expression. This is the absolute value, g of f of x minus g of f of c divided by x minus c, absolute value of it. We are considering the supremum of it with condition 0 is less than absolute value of x minus c is less than delta. Now remember, this is the same expression for which we are trying to find the limit as x approaches 0 to find the g composed f prime of c. So we need to evaluate this. We kind of want to investigate the limiting behavior of this expression. If we can find the limit of this limiting behavior, or in this case the supremum for this expression, and if it happens to be something 0, then we are done. Okay, so let's go ahead and talk about it. So this is the condition, this is the supremum I'm trying to evaluate. Now that's the same as this, except I have added a new condition. F of x minus f of c is not equal to 0. Okay, that's the condition I am adding. Why that should not make a difference? Look, if f of x minus f of c is equal to 0, then g of f of x minus g of f of c is going to be 0. Because if f of x is equal to f of c, then g of f of x must be equal to g of f of c, giving me the numerator to be 0. In that case, the whole thing collapses and absolute value of 0 is 0. When you're taking absolute value of any number, okay, any real number in this case, the smallest value you could have is 0. It cannot be less than 0. So if we are tossing out some points, right, from this set of data points, but we are tossing out the points that are the absolute minimum that this set could have. So when you are finding supremum for a set and you are tossing out some of the numbers from the set which are absolute minimum, that should not have any impact on the supremum. That means it's not going to change the supremum. So that's what it is. Now what I'm going to do, I'm going to take this expression and exactly what I did the last time. I'm going to divide and multiply by f of x minus f of c. Okay. Now, supremum of these two products. These conditions do not change. Now, we know that G, by the way, we know that G has derivative. G has derivative at what point? F of C. So that means G must be bounded. G must be bounded. What does it mean for it to be bounded? Bounded means there is a big number, okay? Let's call it some big number m. So this expression, this first one, okay? This first ratio is not gonna be more than m, okay? It will be less than or equal to m. Now, then, of course, this ratio, by the way, all right, is nothing but the derivative type of ratio, right? F of x minus f of c divided by x minus c. But we found that f prime of c is equal to 0. We just showed it, right? If that is the case, by the way, we could make this ratio arbitrarily small. So you have a fixed number, okay? This is bounded means absolute value of this guy is gonna be less than some number, okay? Some fixed number m. Again, think about the absolute value. When I say bounded, I meant that absolute value of this ratio is less than some fixed number m, okay? Now, some fixed number times arbitrarily small number. So that means, let's say m is the fixed number times arbitrarily small number. Let's call it 1 over n. N is the number, let's say n is integer. I can make, this one doesn't change, but this one changes. So I can make it as small as I want, as small as I desire. So 1 over n could be 1 over 2, 1 over 3, 1 over 4, 1 over 5, as small as I want. And the limiting value of this is going to 0, 1 over n, which will force the entire expression to go to 0, which just tells me that this supremum is nothing but 0. Oh, by the way, this supremum is the supremum of this guy, right? G of f of x minus g of f of c divided by x minus c. That is the same ratio that we use to find the derivative of the composition function, or g of f of c, g of f prime of c. So that ratio has supremum or extreme high value, value to be 0, which in essence says that g composed with f prime of c must be equal to 0. Using the definition that we have written above, I have written it down here again, that should give me 0. So the derivative of the composition of g and f evaluated at c is equal to 0. So whenever my f prime of c is equal to 0, the entire composition derivative of the composition function g composed with f prime of c is also 0. So therefore I am okay. So no problem when f of x minus f of c could be 0. So that covers both scenarios. When f of x minus f of c is not equal to 0 for any value of x in any neighborhood of c, then we are good. The first case, easy case. But the case where it is equal to 0, we are still good, because we showed that in that case the derivative could be 0, f prime of c. That will bring the g composed with f prime of c to be 0, as well. So we covered both cases. That proves the theorem, the chain rule for derivatives. So the chain rule for derivatives is the derivative of composition of two functions. And you can extend this idea to more than two functions. So that should be straightforward extension. I hope that this discussion was helpful. Thank you very much.